The next speaker is Barrett, and I'm curious about the title.
Actually, I've forgotten what the title is. It'll be up in a minute.
Look at the screen and go.
No signal.
From experience, my computer is a bit funny. It really hates it if it's already switched on and you plug in the projector thing. So I have to plug this in first and then start it up. And of course it takes a minute to start up, so that's just what it's doing now. It won't be long.
Why don't you take questions before the talk? But you don't remember the title, right?
Here we are. The talk's quite short, actually, so if that's any consolation for the wait. So I won't keep you too long. Escape key to cancel. There's my title. What is the quantum state from beginning? There we go at last. Sorry about that. Alright, well, I'm Jonathan Barrett from Royal Holloway. I'm going to talk to you about a fairly recent result that we put on the archive back in November. It's a novel kind of no-go theorem for quantum theory in the same sort of class as Bell's theorem. These are my collaborators here, Matthew Pusey and Terry Rudolph, both here, both from Imperial College. Of course, the theorem has already had quite a lot of discussion and so forth on the internet and blogs and things, so I hope at least a few people in the room aren't bored of it yet. Okay, so the idea is somehow to address this question of what is the quantum state, and it's stated a somewhat vague question, and there have been somewhat vague debates raging about this going back to the very beginnings of quantum theory. In order to provide some motivation for thinking about this a bit better and a bit more carefully, here is Ed James. But our present QM formalism, he writes, is not purely epistemological. It is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelette that nobody has seen how to unscramble. Yet we think that the unscrambling is a prerequisite for any further advance in basic physical theory, for if we cannot separate the subjective and objective aspects of formalism, we cannot know what we are talking about. It is just that simple. And this work is supposed to be some sort of contribution to that project, the project of unscrambling those parts of the formalism which are to do with describing reality, and those parts which are to do with agents' information about reality. To begin though, it's useful to begin, I think, just to fix some ideas by discussing something that we do understand already and we do know about, and about which hopefully there's no controversy, and that's classical mechanics. So let's think about classical mechanics, and let's consider a single particle moving in one dimension. At any given moment of time, the particle has some definite position and momentum, and in fact the state of the particle is completely determined by the values of x and p, and we can represent the state of a particle like this. Of course, there's phase space, two-dimensional in this case, with axes x and p, and then the state of the system at time t is a point in the phase space. And as time goes on, the particle moves around, so its state changes, so this point moves around in phase space, and the motion is determined by Hamilton's equations, which look like that. Q dot equals dh dp, and Q dot is minus dh dq. Of course, the particle does have other physical properties, apart from position and momentum. For example, it has an energy, but these other physical properties are functions of x and p, so we would write something like the energy is h of x and p. It may also have other properties like mass, say, or charge, which don't change, which are also physical properties, but we can regard those as constant functions of x and p. Now, sometimes we don't know the exact microstate of a classical system. We might not know the exact positions and momenta of all the particles, but the information that we do have defines some probability distribution rho over phase space. So Here's an example again of a single particle moving in one dimension, 2D phase space. This is supposed to be a probability distribution on phase space. These are contour lines here. These blue ones representing the probability distribution. Now here's the point. That distribution, rho, it's not a physical property of the particle in the way that x and p and energy and mass are. After all, the particle on the dial here occupies some definite point in phase space. It has its definite values for x and p. And the particle itself, that doesn't care in some way what probabilities I'm assigning to the different states. Those probabilities are just a function of my own ignorance of the true state of affairs here. Nonetheless, we can do calculations with these probability distributions. We can calculate how they evolve in time, for example, and the evolution of the probability distribution itself obeys a deterministic law, which is Albert's equation down there. Okay, so what to take away from this is that there are two very different kinds of thing here, two very different kinds of state. There is the actual physical state of the particle, x and p. Let me introduce some terminology. Let's refer to that as the ontic state of the system. Ontic from Greek and meaning to do with what exists. And then the probability distribution, we'll refer to that as an epistemic state. Epistemic meaning to do with knowledge. And if we stick to this terminology, we'll never get confused between the two. Okay, so much for classical mechanics, and like I said, I hope that's clear and that there isn't any controversy about any of that. So, what about the quantum state then? So back to the title, what is the quantum state? Roughly speaking, there seem to be at least two possibilities. One is that it's ontic. It's an ontic state, a bit like the point in phase space of the classical particle. For example, if we're talking about a quantum system with a wave function, we might think of the wave function as a real physical wave of some kind. And I think the main argument for that is that quantum interference seems to be most easily understood this way. If we think about something like the two slits illustrated here, the most natural way to understand the fact that we get an interference pattern seems to be that there just is some kind of physical wave interfering. Of course, if it is a real physical wave, it's a bit of an odd one. It's not some wave that just floats around in free space, because the wave function is defined on configuration space, and not on the three-dimensional space that we live in. But still, maybe that's okay. The other possibility that we want to think about is that the quantum state is actually an epistemic state, more analogous to those probability distributions in classical mechanics than it is to points in phase space. The idea here is that a quantum state would encode an experimenter's knowledge or information about some aspect of reality. So here is a quantum state psi, here's an experimenter, and psi in some sense is in the mind of the experimenter. It's a description of the experimenter's information. I mentioned one reason why we might think that the wave function is ontic, and that was a sort of slightly vague one to do with understanding interference in a natural way. But here are some arguments for thinking of the quantum state as being epistemic. And the first one of these, and perhaps the most compelling, is that of collapse. Collapse of the quantum state when we do a measurement. If the quantum state is epistemic, then collapse doesn't need to be puzzling. It's not some kind of weird physical process that happens and is non-local and for which we don't have a good definition of exactly when it happens, and so forth. Collapse, on this view, need be no more mysterious than the Bayesian updating that we do to a probability distribution when we get new data. And here's an expression of that kind of view. This is Bill Unruh. He says the wave function is not a thing that lives in the world. It is a tool used by the theory to make those inferences from the known to the unknown. Once one knows more, the wave function changes, since it is only there to reflect within the theory, the knowledge one assumes one has about the world. Okay, but it's not just about labs. Here are some other arguments for the wave function being epistemic. And these are to do with the quantum state just behaving very much like a classical probability distribution in many ways, as we know from quantum information theory. So, for example, non-orthogonal quantum states cannot reliably be distinguished. That is, you can't determine which is which with certainty in a single shot measurement. In that, they are just like probability distributions. Another thing is that quantum states are exponential in the number of systems. Because if I have n systems, then the joint state is defined on the tensor product of all those n Hilbert spaces. And that means the number of real parameters I need to write down to specify that quantum state is exponential in the number n of systems. That's also just like probability distributions. And in fact, this is just what we'd expect, this exponentiality. If a quantum state represents knowledge of information of some kind, to my mind at least, it's a very sort of surprising and puzzling thing if this quantum state is ontic, if it has a direct image in nature somehow. It is surprising that nature would actually have this kind of exponential complexity, but not surprising at all if the quantum state is epistemic.
Can I ask you
Yes.
a rather stupid question? Why in the classical mechanic we were happy that it could be both of the ontic and epistemic? I mean, you show it, there is no controversy, it could be ontic, it could be epistemic, depending on what you're presenting. So why in the quantum world it needs to be one of those two? Why it cannot be both?
I'm not sure what it would mean for something to be both.
But
And in the
exactly
classical
like-
case, we didn't have anything that was both. We just had the ontic states on the one hand, and the epistemic states, the probability distributions on the other hand, and we understood the difference, and they were two different things.
Different representation.
There are two different representation of the same thing, so why could not be... I'll stop here, this is a discussion.
I'm not really talking about representations of things. I'm talking about the actual physical state of a system. That's physical. And okay, it's represented by a mathematical object, which is a point in phase space. And on the other hand, we have the information possessed by an experimenter. And that's a thing in the world, but it's nothing to do with the system. It's in the head of the experimenter. And that's represented by a mathematical object, which is the probability distribution over phase space. Does that help? Serge?
I had another question about your previous transparency. You said that the epistemic point of view could help understanding the collapse of the wave function. But are you not invoking determinism there by saying that you want that actually there's some extra knowledge which will determine in advance how the state will collapse, but then, or not? Because if you ask the models to be deterministic, then we know we run into those problems with Bell's theorem. So why is that and the reason to invoke epistemic states not running into a contradiction with determinism?
I'm not convinced that this argument really requires one to assume underlying determinism. But maybe we don't need to address it now, because part of the point here is that although these arguments, all of them are sort of suggestive, they are also all vague. And part of the aim here is just to say something precise instead. So rather than arguing about the vague argument and whether it means determinism or not, it might be better just to sort of leave it vague and get onto the precise thing. Okay, and the final one that I had on this list was some other properties of quantum states, but again that they share with probability distributions. They cannot be closed, they can be teleported, and so forth. Okay, and here's what I'm going to show. And here and that with the theorem. If the quantum state psi merely represents information about the objective physical state of a system, then predictions are obtained that contradict those of quantum theory. So let's see how we do that in more detail. Suppose, first of all, that a system does have an ontic state. That is, suppose that a system does have an objective physical state which is independent of the experimenter and independent of which measurement someone decides to perform later on. And let's just give that ontic state a label. Let's call it lambda. Let's also suppose that if I do perform a measurement on the system, there are some probabilities for getting different measurement outcomes, and these probabilities are determined by the physical state of the system. They're determined by lambda. So if we do a measurement M and it has an outcome K, we could write down the probability of K given measurement M and ontic state lambda. Now, this to emphasize, I'm not assuming very much at all about this physical state of the system. I'm not assuming, for example, that it's like a classical system. I'm not assuming that it has a definite position or a definite momentum, or even the position and momentum are the right sort of degrees of freedom to describe the system at a fundamental level. I'm not assuming determinism either. All the physical state does is determine the probabilities for these measurement outcomes. Those probabilities don't have to be 0 or 1. And I'm not assuming that all observables have a definite sort of underlying value or anything like that. Okay, and the other thing we're going to suppose is that a quantum state psi then actually describes an experimenter's information about this objective physical state lambda, which formally I will take to mean that psi corresponds to some distribution, mu psi, over the different values that lambda can have. So here's that summarized. This is a schematic picture of an experiment. We have an observer over here and a device that prepares a quantum system. And the experimenter knows enough about this preparation device that, given and about quantum theory, that when he uses this device to prepare a system, the experimenter associates the quantum state, let's take it to be a pure state psi with the system. But we're assuming that after it's been prepared, the system has some objective physical state, lambda. And it needn't be the case necessarily that the same value of lambda is prepared every time when we use this preparation device. So as we were saying, psi corresponds to some distribution over the possible values of lambda. And then a measurement is performed and there's a probability of getting outcome K, which depends on the measurement M and on the lambda. And of course, there's some condition that ensures we actually recover the quantum predictions here. So assuming this is a von Neumann measurement, the quantum probability is mod squared of the overlap of psi and a ket K. And we should recover that probability if we integrate over all the values of lambda according to the measure mu over lambda multiplied by the probability of getting outcome K. Okay, fine. So that's the setup, that's what we're talking about. Now, so far these assumptions are actually similar to those of Bell's theorem. This is pretty much the first things that one says when setting up Bell's theorem. But the difference is that when doing Bell's theorem, there is then an assumption of locality that is imposed on these ontic states, on these lambdas. And I'm not going to assume locality, because we're not talking about locality. I'm going to assume something else instead, which I'll need for the argument in a few minutes, which I'll call preparation independence. It says this: suppose we consider two completely independent preparations of quantum systems, one of which prepares a system such that the associated quantum state is psi, and the other of which prepares phi. And suppose that these are isolated systems, and that quantum theory associates pure states, psi and phi, to these systems. And being independent, the quantum joint state of the two systems will just be the direct product, psi tensor phi. Now when I say these are independent, we can take this to extremes if we like. You know, one could be on Earth, one could be on Mars. They've really got nothing to do with one another. So the assumption of preparation independence says that in this case the ontic states of these systems will be uncorrelated. So here's the psi preparation, we get an ontic state lambda 1. Here's the phi preparation, somewhat different, we get an ontic state lambda 2. And formally, preparation independence says that the overall distribution here over lambda 1 and lambda 2 for these two systems is just the product of the individual distributions, mu psi of lambda 1 and mu phi of lambda 2.
But this means that any ontic state has a unique preparation step? There's only one way to prepare a particular ontic state?
No, I'm not assuming anything like that.
So when you say if I have two lambda 1, lambda 2, which are different ontic state?
Well, okay, sorry. So actually lambda 1 is supposed to represent the ontic state of this system over here, system 1 let's call it. And lambda 2 is the ontic state of this system over here, let's call it system 2. But I haven't said anything so far about the actual values of lambda 1 and lambda 2 and whether they can have the same value and so on. And actually that is what I'm going to talk about next. So this is a kind of locality condition in a way, because we're saying that, amongst other things, that the choice of which kind of system to prepare here, the choice of what quantum preparation to do, doesn't affect the ontic state over here. But I'm not assuming this for entangled states or anything like that. It's a much weaker kind of locality than you need in Bell's theorem, because it only is assumed to apply to these systems that have never seen each other, nothing to do with one another in the quantum product state. Okay. And now here's the point, and now this is related to what Alvin was just saying. Suppose that we do have some kind of model along the lines I've been describing. But suppose it happens in this model that actually, for every pair of distinct quantum states, phi and psi, those distributions, mu phi and mu psi, do not overlap. So here's a picture of this. This rectangle, called it big lambda, that's supposed to be the set of all possible ontic states, the set of all values that little lambda can have. And this blob here, that represents the distribution mu phi. So actually the blob is the support of mu phi. So mu phi is positive all over this blob and 0 everywhere else. That means that when I prepare a quantum system in the pure state phi, I have some probability to get any of the lambdas in this region, with 0 probability to get a lambda anywhere else. On the other hand, if I prepare a quantum system in pure state psi, I have some probability to get a lambda anywhere in this region, 0 probability to get lambda anywhere else. So if this is the case in particular, that does mean that if I prepare one system in state phi and the other in state psi, there is 0 chance that the ontic states of those two systems are actually the same. Okay, now what can we say about this? Well, first of all, the quantum state can be, in this case, inferred from the ontic state. My ontic state is a particular lambda, that's a particular point in here, say here. And there's only going to be one quantum state phi, such that lambda is in the support of mu phi. And it's assigned probability 0 by all other quantum states. So knowing lambda, that means I can actually infer what preparation phi must have been. And from this I say that actually, in this kind of model, it may appear the way we've written it, that lambda is the physical state of the system, and the quantum state is knowledge about lambda. But actually, what we should actually say in this case, at least, is that the quantum state is a physical property of the system, and is not mere information. I'll come back back to that in a second. The other case, of course, is when sometimes these distributions do overlap for distinct quantum states. So here we have the supports of mu phi, here the supports of mu psi, they overlap, and there's at least some quantum state number 0 in the overlap region that's compatible with both of them. And for example, if you have a system in that quantum state under naught in this case, you would not be able to infer with certainty whether the quantum state phi or psi had been prepared. Okay, and what I'm going to show is actually that in this case you end up with predictions different from quantum theory. But just before I do that, it's perhaps worth just dwelling on this a little bit. Why do I care so much about whether these distributions overlap or not? Why am I taking this as an important thing? And how did I so quickly make this leap from quantum state can be inferred from the ontic state, disjoint distributions, to this sort of grand-looking statement at the bottom? Quantum state is a physical property of the system. Well, the point really, I mean, the idea is that, let's think again, let's return to this classical case. Remember I was saying that in this case, physical properties of a particle, like energy, are functions of the ontic state. And actually, I think a good definition of physical property is that any function of the ontic state would be called a physical property of the system. So that's what I'm appealing to, really, when I say here that if you can infer the quantum state from the ontic state, like you can here, then the quantum state is a function of the ontic state. And by that definition, that means that it's a physical property of the system.
John, it
Yes?
seems to me that your states are in, say, two different locations, or at least they're two different states. So these two different lambdas naturally reside in a different space, in a different computational space. Whatever. Are you therefore needing to assume things like homogeneity of space and homogeneity of time in order to have a notion of lambda 1 being equivalent with lambda 2, or being equal to lambda 2? Because at the very least it seems that you've applied some kind of morphism from the parameterization of one system of states to the parameterization of another, and that morphism would be suggestive of some symmetry in physics.
Can you repeat the question?
Well, yeah, so the idea really is that if you're talking about lambda 1 being equal with lambda 2, then how can you refer to two things being equal unless they're resident within the same space? But they're not resident within the same space if you're treating these two systems as being independent and distinct. Therefore, equality is given by some homomorphism from the configuration space of the one to the configuration space of the other, inquiring as to whether the complexity associated with that homomorphism is owing to, or rather the simplicity of that homomorphism is owing to some symmetry that's being assumed in physics, if one needs to think about these issues, or if this is not relevant. I don't know.
I think it is relevant. They sound like very good issues to think about, and I've not thought about them particularly. I mean, part of the answer here sort of might lie within this sort of word system that we've been throwing around. I mean, of course, a system really just means whatever it is that we're focusing our attention on. So if we're talking about the spin of a particle, system might just refer to the spin degree of freedom. And the quantum state, if it's spin half, might just be intervening two-dimensional Hilbert space. I mean, of course, there is a sort of wider system there that has other degrees of freedom.
But the idea that one particle is in spin up and another particle is in spin up means you've got a notion of parallel transport of what up is from one place to another, and it also means you're assuming that the particles are identical, presumably. So there seems to be a lot of physics going into this before you get. The example of spin, sure.
assume that this combines all possible lambda here with Mars and everything.
But then you need one lambda to describe the universe, and I think in that case the argument's going to fail because the argument has to do with the idea of there being two different lambdas that might be equal.
No, but the two lambdas are in different spaces. They just put together as a Cartesian product.
Yeah.
The thing that you need, which I don't know how it transforms into homogeneity, is just that there are two experiments which, in quantum theory, you would assign.
I'm happy with the
Same
Cartesian
sign.
product. I'm worried about where John writes lambda 1 equals lambda 2 on the next slide.
Well, there are two physicists in these different places doing different experiments, but who are just using the same mathematical model to describe each of their experiments. And that mathematical model involves a space of possible lambdas. Just as if they were just doing standard quantum theory, they'd be using, let's say, the same mathematical model, which might be a two-dimensional complex Hilbert space. And then we're sort of comparing the two in that way. Let me sort of offer that as my response for now, and can carry on. But it's I think there's some stuff that deserves more thought there, I think. Okay. So I was distinguished two cases, overlapping versus non-overlapping, and argued that in this case we actually can reach the conclusion that the quantum state is a physical property of the system. In which case the quantum state is ontic, or it's part of the ontic state, at least. Even here, of course, it wouldn't necessarily follow that the quantum state is a complete description of the system. The question of whether one could add additional variables to it is still completely open. Because one could have a range of different values of lambda here, all corresponding to the same quantum state. Okay, so let's just do the proof now then, which says that if this is the case, then you get different predictions from quantum theory. I guess a little credit is due first of all. These distinctions that I'm describing in terms of overlapping supports were first made rigorous by these people, Harrigan and Speckens, in a paper that Lucy and Harding via private communication, and for another paper on related stuff that I won't go into, so this one by Alberto Martina. So here's the no-go theorem. So in order to derive a contradiction with quantum predictions, let's suppose that there are distinct quantum states. Instead of phi and psi now, it's helpful to call them phi naught and phi 1, with overlapping distributions of an ontic state lambda naught from that region. And suppose that the probability of obtaining lambda naught when the preparation is phi naught is bigger than some q, which is bigger than naught. Probability of obtaining lambda naught given preparation phi 1 is bigger than q, which is bigger than naught. Now I'm giving you a sort of simplified version of the argument here, because when you do it properly, this space of lambdas might be a continuum, and you deal properly with the mu's as measures on the continuum. You might not have a finite probability of an individual lambda like that. All that can be done properly, but I'm going to be doing a slightly simple version. Okay. Now here's what we do. Suppose we compare n systems independently, where n is to be fixed a bit later on. And each of those systems is going to be prepared in either the quantum state phi naught or the state phi 1, which means altogether there are 2 to the n possible joint states that I might be preparing here, each of which is a direct product. So I might have phi naught, phi naught, phi naught every time, or all phi naughts except the last one, which is a phi 1, or all phi 1s, and so forth. The 2 to the n possibilities. Here is all of that in a picture, imagining the preparation device, so you can move a lever left or right to either prepare phi naught or phi 1. And when you do that, out pops a system which has some ontic state, lambda 1 for the first system, lambda 2 for the second system, and so on. Okay, now we appeal to that assumption of preparation independence that I was talking about. what that assumption gives us is that for any one of those 2 to the n possible product states, that's my preparation, then there's at least some chance. But it happens that every single one of these n systems actually emerges with the ontic state lambda 0. And lambda 0 was the one from the overlap region, remember. So what we now have is n systems all in the ontic state lambda 0. And appealing to the assumption of preparation independence, the probability of that happening is at least q to the power n, given that the probability of getting lambda 0 is at least q for a single system. Okay, and now here's the problem. So this is why we get a contradiction. For large enough n, there is some entangled measurement that you can do across all of those n systems. And it's a Neumann measurement. It has 2 to the n different outcomes corresponding to projectors P1 up to P2 to the n. And the measurement has the following property. If the state prepared was the direct product all phi zeros, the probability of getting outcome P1 is actually 0 according to quantum theory. On the other hand, if my preparation was actually every system in the state phi 0 except for this one, which is phi 1, in that case the outcome P2 of this measurement has probability 0 according to quantum theory, and so on. And for every single one of these possible product preparations, one of these outcomes has probability 0. And for every one of these outcomes, it has probability 0 on one of the preparations. Okay, now this kind of measurement was considered before in a different context by these people, Hayes, Fuchs and Schaff. But here's the problem. I mean, as I've just been arguing, for any one of these 2 to the n product preparations, there is some chance that the ontic state you get is actually just every system in the ontic state lambda 0. So what happens? So suppose the systems are all in the ontic state lambda 0, and they come, and here's the measurement device, and it sees the ontic state lambda 0, lambda 0, lambda 0 every time. The measurement device has to produce some kind of outcome. So what should the probabilities for these different outcomes be, conditioned on the ontic state being this one, all lambda 0s? Well, we can argue actually that for any one of these PI, that outcome should have 0 probability on this ontic state. For example, when the quantum state is the product phi 0 every time, there is some probability that the ontic state is this lambda 0 every time. And if that ontic state gave finite probability to P1, that would mean that we sometimes got the outcome P1 when we prepared this state. And quantum theory says that shouldn't happen. It has probability 0. And so on for all the other possibilities here, until we conclude that if this is the ontic state, all lambda 0s, all outcomes should have probability 0. But of course they do have to sum to 1. These are probabilities for the different outcomes of the measurement, and that's the inconsistency. So that's it. That's the conclusion of the argument. If those mu's overlap, we get different predictions from quantum theory. Here's how to do that measurement. I said that n would be fixed later. Well, fix it like that. Without loss of generality, let's write our quantum states in a certain way, and then let's do this circuit here. What one can show is that if one does this circuit here, and if each of these is just a basis measurement, that measurement has all the properties of the one I put on the last slide. These gates are Z rotations, determined by some parameter beta. This is an entanglement gate, determined by some parameter alpha. And the point here is that for any pair of quantum states, phi 0 and phi 1, if you choose n large enough, you find suitable alpha and beta such that this circuit has the required properties. Good. So that's nearly it. Of course, in a real experiment, you won't verify exactly that certain outcomes have probability 0, there'll be noise and so forth. Suppose that you do a real experiment and you end up with some data that is consistent with probabilities being within epsilon of quantum predictions. Well, in that case, you can deduce this. This is a bound on the classical trace distance between the distributions mu0 and mu1. So the distributions corresponding to the two distinct quantum states. It's given by this. What we see here is that if the noise epsilon is small, this is close to 1. And if the classical trace distance is exactly 1, that's when the two distributions have no overlap at all. And if it's approaching 1, then in some sense you're getting close to that situation. Okay, and just to finish off now, I mentioned at the beginning that this is a no-go theorem, and that as such it's in the same class of results as Bell's theorem. Here's a kind of comparison. Bell's theorem assumes that systems have some kind of objective physical state, and it makes sense to write it down and to denote it lambda, let's say. Bell's theorem also assumes that experimenters have free will to choose their settings in a way that's uncorrelated with the lambda. And then if you also assume the results of quantum theory, you get non-locality. Here's what the new theorem says. Again, we assume something similar. The systems have this objective physical state lambda. We have the preparation independence assumption that I was talking about. And if we assume the results of quantum theory, that rules out the psi-epistemic models, the ones with the overlap. And the conclusion is that the quantum state is ontic. Okay, and this is the last slide, just some final sort of interpretational remarks. What does this mean? What do we do with this? Well, we've learned that a quantum state, whatever it is, it's not the experimenter's information about the objective physical state of a system. Here are some possible responses to that, which I divided into 3. One is just to deny that the initial assumption we made that systems even have a thing that you could call an objective physical state. A quantum state in that case you might hold is experimenter's information, but it's information about measurement outcomes, not about an underlying physical state of the system. Here's a second response. You could just accept all the assumptions and the conclusion of the theorem. You could say, yes, the state vector is a physical property of a quantum system. The wave function is of some kind of real wave, perhaps. This view runs into some problems. If you think that the quantum state collapses sometimes, then again, now that's mysterious again. Collapse is non-local, it doesn't have a well-defined time of occurrence, and so forth. Schrödinger's cat appears mysterious because both live and dead cat are sort of there in this wave, which is a real wave. You can't interpret it as someone really lacking information, whether the cat's dead or alive. And a third kind of response is to not believe in some of the other assumptions of the theorem. So you evade the conclusion by not accepting all of the assumptions. So, for example, you could try to construct realistic physical models where that preparation independence assumption doesn't hold. So the people have suggested retro-causal influences in that regard. Imagine some sort of causal process that starts at that final measurement and propagates back to the proper preparations. It would be easy to imagine that the preparation independence doesn't hold. Other people have talked about relational properties. I think I'll come to that. And I'll stop there, thanks.
So thanks. Some further questions?
So, I have some trouble with the case of an entangled part. I'm saying, in the case of entanglement, because how can you assume that you have this separation? The only way to be sure that this is true is that you have to prepare pure states. The only way to prepare pure states is to make a von Neumann measurements, whatever done unitary, but still anyway a von Neumann measurement. At the end, you are left with classical states. So particle A and particle B, you are sure a priori that they are not entangled, so that this probability is factorized only if they are in a possible set of classical states, particle A, in a possible set of classical states, particle B, and now everything is ontic for sure. So how can you say that there is an ontic state for a particle if the particle is entangled with another one? This is something which I don't understand. I'm missing something.
I'm not sure I followed all of the first part of what you were saying, but let me address the very last thing. What if a particle is entangled with another particle? Does it make any sense to associate an ontic state with each of those particles separately?
Right. That's the point.
The answer is maybe, maybe not. I can imagine a theory, at least, where each particle gets its own ontic state, and then there is explicit non-locality between them to recover Bell correlations. But it could also be that when systems are entangled, they don't have their own individual ontic states. It's only when they're isolated that they do. So a good example of that is bone theory, where what I've been calling the ontic state. In bone theory, that's the pair. It consists of the wave function and also the positions, because the wave function is part of the description of the system, so are the positions. So the complete ontic state involves both of those things. And when they're entangled, that wave function part of the ontic state is entangled, and so the overall ontic state doesn't have a product form. But nonetheless, in bone theory, when I have independent, isolated systems, we can regard each of them as having its own ontic state. Each of them has its own pure wave function and its own position, separately from one another. And in order to prove this theorem, I only need to assume that systems have independent ontic states for isolated independent product systems. I don't need to assume that that same thing holds for entangled systems.
Mention quickly, I think you also in this later version of the paper falls in which of these categories? The one that now quantum state can be interpreted.
Oh, that.
Is it?
It shows how to. So yes. Let me backtrack a little. An interesting question here is whether you could make this same argument more simply. Could I make an argument, perhaps without using the preparation independence, without invoking multiple systems, without a complicated entangled measurement? Could I still then make an argument that actually, if you want to recover predictions just for a single system, you can't have any overlap between those distributions. So that it was an interesting and open question, and we've known for a long time that there do exist models, at least for qubits, which are psi-epistemic, meaning that there is overlap. Okay, so if all you want to do is model measurements on a single qubit, you can find a model which is this kind. The distributions for different quantum states overlap. One such model was written down by Koshin and Specker a long time ago. But the question that was open for higher dimensions, and what that more recent paper chose, if we gave the opposite title, is that if you only want to have a model for a single system, reproduce probabilities for measurements on that single system, then actually you can find one in any dimension, not just qubits. which has this overlapping property. Now, okay, if you want to, you can sort of extend you can, given n systems, you can always regard them as one big system and apply the model for that one big system, but it won't satisfy that preparation independence.
So maybe one quick question before we...
So the quick question is, the theorem proves that there is no overlap between these probability distributions. The question whether quantum mechanics is still extendable, is it in a sense that if I would condition on some hidden variable from this probability distribution for one quantum state and get some better predictive power, is it still open? It's not covered with this theorem.
It's not covered by this. So everything I've said is completely compatible with the idea that there could be a range of different lambdas associated with one quantum state phi. That's why I have a blob here rather than just a delta function. And those lambdas could give more information than just phi on its own. And bone theory is an example of such a thing. There is one result which is due to Kolbeck and Renner. And they show that, under some assumptions of their own, the quantum theory cannot be extended in that way. So there cannot be any variable, they say, that gives more information than the quantum state on its own. But they make an assumption which we don't. And in their paper they simply refer to it as free will of the experimenters, which sounds like something very natural you have to accept. But if you look a bit more closely at what they're doing, that condition, which they call that, actually involves a kind of no signalling assumption, which is taken to hold not only operationally but at the level of the hidden variable. So that's how bone theory gets around it, for example. Yeah. So with that assumption, then you can show that you cannot extend quantum theory.
Okay, I think if there are further questions, we can do that on the break. So let's thank the speaker again.